With Fred and I taking a little bit of a break, we thought it'd be great to dig into the archives and see what sort of stories really captured the imaginations of people around the world. Things like opening up moon rocks 50 years after they were collected. Other things like the first photographs taken by James Webb or the first image of Sagittarius A star. Those are the kinds of things we've been talking about over the years. So sit back, relax, and enjoy archival episodes of Space Nuts.
Space Nuts.
Hi there, thanks for joining us on another edition of Space Nuts. My name is Andrew Dunkley, your host, and today on the program we are going to be talking about the big news of the week, probably the big news of the year, and that is the first official image from the James Webb Space Telescope. It's only been announced in the last hour or two since we started recording, so it's fresh off the press or off the president's desk, whichever way you want to look at it. And Alex from New South Wales is apparently going to ask a question about the size of galaxies. That's all to come on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9... Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining us, as always, is Professor Fred Watson, astronomer at large. Hello, Fred. How are you?
Very well, thanks. Very excited with all that's going on.
Oh, man, it's just crazy town at the moment.
Well, it is.
The astronomy world is agog.
Agog, that's right.
Agog. It's not a word I get to use very often.
No. Yeah, I like agog. I think it's got a ring to it.
We'll get to that in a moment. Of course, we've got plenty to talk about and some audience questions, as I mentioned. And you've got a studio guest, Fred. Are you able to share this with our viewing audience? If you're watching us on YouTube, get ready for a surprise.
It's to let everybody know that he still exists. There's Muscat, our family cat, who normally doesn't come into the study here because he leaves copious quantities of hair wherever he goes. But he's been asleep there in the chair all morning and most of the afternoon, so he's still here. He doesn't say much these days.
He's doing his hats proud because that's what cats do best.
Yep.
It's good to have Muscat in the studio. Right, let us get down to business. And first on the agenda is this amazing image that has been delivered by the James Webb Space Telescope. It's been a lot of anticipation about what the first image would be, a lot of anticipation about how far-reaching the James Webb Space Telescope will be in its capacity to provide deep field imagery from far, far back in the universe, and it has not disappointed, Fred.
Not at all, that's right. So what we're seeing, and I would guess most of our listeners will have seen this because I think it's going to be the cover picture on the podcast for today.
Yes,
it really is a beautiful image of a cluster of galaxies, which, as always, has a gobbledygook name. It is SMACS 0723. SMAC stands for Streaming Motions in Abell Clusters.
Okay.
And Abell clusters are clusters that were catalogued by George Abell, who I knew when he worked in Edinburgh for a while. So cluster is a cluster of galaxies. But of course, like so many of these giant clusters, its mass acts as a gravitational lens, magnifying and distorting the images of galaxies in the far distance behind it. And so this particular cluster shows up beautifully in, the kind of colours that you would expect. So, as you know, the James Webb Telescope is an infrared telescope. Excuse me. So it can look at the image in various infrared wave bands. And what you can do is sort of equate those to visible light wave bands so that things that are in the far infrared show up as red in the visible. Things that are, in the mid-infrared show up as white. Things that are in the near infrared, in other words, not much redder than red, they'll show up probably as blue. I'm not quite sure how they did the colour balancing in this image, but they've got it absolutely right because the nearby stars are blue, the relatively nearby cluster of galaxies is white, and the distant ones, as you might expect it, because they're highly redshifted, they look orange in colour, and again distorted. So we're looking back here, it will be, well, the nearby cluster is 4.6 billion light years away. The one beyond it could be double that. I haven't seen the results of that, but it's a long way off. And what I think is most telling about this image, so this is being called Webb's first deep field image. And you probably remember, because we've talked about it before, the Hubble Telescope produced a number of deep field images, deep being how far into the universe you're looking, how far into the past you're looking. Yep. And there was the deep field, the Hubble, I can't remember what, the ultra deep field I think was the last one. There were a number in between as well. But they took weeks of time on the Hubble Space Telescope to build up the imagery. I remember the first one, they chose the part of sky because there was nothing visible in it. And so they observed it for several nights or several days, because it doesn't matter in a space telescope, and finally got these deep fields. But it took up to weeks to get them. The James Webb first deep field was obtained in 12 hours. So that's telling you that, we now have a tool that can beat the pants off the Hubble Space Telescope, and that is no small achievement. And of course that comes about because it's a much bigger telescope. The Hubble is 2.3 metre telescope. This is a 6.5 metre telescope.
Yeah, it's and that's really part of the reason why people have become so excited in anticipation of what it is capable of, and it's already showing its true colours. Boom, boom. You know the part that really blew my mind when I looked at the image and read the description from NASA? I'm sure you'll know what I'm talking about here. NASA says this image covers a patch of sky approximately the size of a grain of sand held at arm's length by someone on the ground.
That's right.
And reveals thousands of galaxies in a tiny sliver of vast space. I know we always talk about the vastness of the universe, but here we are looking at a distance of maybe 4 to 8 billion light years, and we're looking at something that only takes up space the size of the grain of sand held at arm's length.
Absolutely.
I mean, my word, it is awe-inspiring. It really is.
Yeah, it blew the president away as well. I don't know whether you saw the NASA broadcast when this was released, but President Biden, you could tell he was absolutely captivated by all this. It's fantastic to see such enthusiasm. And of course, Andrew, this is only the first of many. By the time our listeners are watching and listening to this, if they watch on YouTube, we expect another tranche of images to have been released. The kinds of things that we're expecting to see, in fact, I think we've got a fairly good list here. We'll see WASP 96b. Now, that is a planet. That's an extrasolar planet, WASP 96b. So it's going to be really interesting to see how that shows up. We're going to see the Southern Ring Nebula. That's a planetary nebula. We'll see, no doubt, a lot of detail in that. We're going to see a cluster of galaxies, a very compact cluster of galaxies called Stephan's Quintet. Very well known, very beloved of galactic astronomers or extragalactic astronomers, people who study the wider universe. These galaxies are physically close together and all interacting with one another. And of course, an object in our deep southern sky, the Carina Nebula, the Eta Carina Nebula, one of the most active regions of space in our local neighbourhood. So it would be really interesting to see what's going on in that too.
Yes, and who knows, we might actually be focusing our cameras on alien civilizations out there somewhere and we don't even know it.
We don't.
That dovetails beautifully into our next story. So all I'll say, just to finish up with the James Webb Space Telescope, is watch this space, as we've said, because there's some exciting things to come. It's really, I think it's fantastic that they've done so well, that it got in place. Yes, it's had a couple of problems that they've managed to overcome without any adverse effect, and now it's ready to do its job. And who knows what we're going to learn, Fred? Who knows?
Absolutely. That's fabulous stuff.
You're listening to, and in some places watching, Space Nuts with Andrew Dunkley and Professor Fred Watson.
0G, and I feel fine.
Space Nuts.
Now we'll go to Alex, who's from a lovely, it's actually a sordid, nasty, horrible little place called Bellingen. In New South Wales. It's actually a glorious part of the world.
Well, it's delightful,
Yeah. Alex is asking about galaxies. This is really good too.
Hi, Fred and Andrew. It's Alex from Bellingen. Congratulations on your 300 shows. May there be many more. Okay, straight into my question. It's about the apparent size of galaxies. It's common understanding that the further away an object is, the smaller it appears to our eyes. I guess you could say the object's angular size reduces with distance. Just look down a long straight road lined with power poles, and the poles appear smaller the further away they are. But I've heard this seemingly obvious relationship between distance and apparent size does not apply to galaxies. Well, it does to a point, but at some distance away from us, the apparent size of galaxies stops getting smaller and then begins to increase the further from us they are. Have I heard that right? And if so, how the heck does that work? Thanks, and keep up the good work. All the best.
Oh boy, you tell us, Alex. That sounds bizarre, Fred.
It does, doesn't it? It's an extraordinary thing, but it is actually true. And it's a real illustration of the fact that we live in a universe that has peculiar properties, and it's basically the fact that we live in an expanding universe that causes this phenomenon to happen. Because if you go through the mathematics, and actually there are places on the web where you can find some nice diagrams that show how this works. The further away you look, you get to a certain point beyond which things don't look any smaller. Because because the universe is expanding. That's the best way to put it. So if you imagine, think about our Andromeda galaxy, our nearest neighbour, which is altogether something like 2 degrees on the sky, at its distance of about 2.5 million light years away. So if you started, we envisage Andromeda, we know what it's like. We've all seen pictures of the Andromeda galaxy, beautiful elongated spiral because it's tilted over towards us. 2.5 million light years away. If you took that galaxy further and further away, of course, it would start looking smaller and smaller because it's getting further away. The laws of physics work pretty normally over small distances. But once you get to a distance which is actually, it's the distance varies because it depends on your model of the universe. But I can give you the technical answer. It's at a redshift of about 1.5. And that's sort of a distance that's measured in billions of light years. We're probably talking about something like 8 or 9 billion light years. Once it gets to that distance, it hits a minimum size, which is about 1,000th of a degree. Remember, it's 2 degrees at its present distance, but it gets down to this 1,000th of a degree mark. And even though then, keep on moving it away, it doesn't actually get any smaller. In fact, it starts getting a bit bigger. And that is totally bizarre. But it's just about the way light behaves in an expanding universe.
Wow. And is this something that would be able to be demonstrated by the James Webb Space Telescope?
Exactly so. I think we'll see physical proof of this happening with the James Webb Space Telescope when they find that there are galaxies that don't seem to get any smaller, even though you're looking at them further and further away. Quite incredible.
That's the same effect I have when I hit a golf ball. It doesn't get smaller or smaller. It stays about the same size,
Yes.
which suggests I'm not really hitting it very far at all. Never mind.
If you hit it
Thank
far
you,
enough,
Alex.
it will start getting bigger. It's coming back to you.
Yes, absolutely. Thanks, Alex, and hope all is well in Bellingen. I know you've been getting rained upon by cats and dogs and camels and who knows what else in recent times, so hopefully it'll start to dry out soon.
Space Nuts.
Hello again, Space Nutters. This is Anna from Astronomy Daily, the podcast stopping by again with a couple of the important stories we've been following over the past week. Astronomers may have finally cracked a long-standing cosmic mystery about one of our galaxy's most intriguing features, the GD1 stellar stream. This ribbon-like structure of stars, which stretches across our galaxy's halo, has puzzled scientists for years due to its unusual patterns of gaps and spurs that seem to defy conventional explanations. A team led by researchers at the University of California, Riverside has proposed an exciting solution involving dark matter, but not just any dark matter. Their research suggests these distinctive features were created by what's called a self-interacting dark matter subhalo, a dense concentration of dark matter that behaves differently than the traditional cold dark matter model we're familiar with. What makes this discovery particularly fascinating is that the density needed to create these unusual patterns in GD1 is much higher than what we'd expect from conventional dark matter theories. The research team found that only a collapsing subhalo of self-interacting dark matter could achieve the necessary density to produce these distinctive features we observe. This isn't just about solving one mysterious structure in our galaxy. If confirmed, these findings could fundamentally change our understanding of dark matter itself. Remember, dark matter makes up about 85% of all matter in the universe, yet we still know remarkably little about its true nature. This research suggests that dark matter particles might interact with each other through a new kind of force, rather than being completely invisible to one another as previously thought. The team used sophisticated computer simulations to model how this self-interacting dark matter would behave, and the results matched perfectly with the observed features in the GD1 stream. It's like finding the missing piece of a puzzle that's been sitting on the table for years, suddenly revealing a whole new picture of how our galaxy works. What's particularly exciting about this discovery is that it opens up new ways to study dark matter. By looking at stellar streams like GD1, we might be able to better understand not just where dark matter is, but how it behaves and interacts with itself, something that could revolutionize our understanding of the universe's fundamental structure. Next, a little mystery from China that has set the space community buzzing. In a remarkable display of technological advancement, China's space program has taken a significant leap forward, conducting tests of 5 different rocket engines all in a single day. The China Aerospace Science and Technology Corporation, or CASC, carried out these tests at 2 separate locations, Beijing and Laiwan County in Hebei Province. One of the most notable tests involved a new hydrogen-oxygen engine designed for upper-stage rockets. During its 100-second test firing, engineers gathered crucial performance data that could pave the way for future missions. This wasn't just any routine test. It's believed to be connected to China's ambitious plans for crewed lunar missions, specifically their Long March 10th launcher program. But that's not all that was tested that day. In Beijing, engineers put 3 different engines through their paces: a main engine, an upper stage engine, and a reaction and orbit control engine. While specific details about which rockets these engines are destined for remain under wraps, it's clear that China is developing multiple launch capabilities simultaneously. Perhaps most intriguingly, the testing day included a methane liquid oxygen engine at the Laiwan facility. This type of engine represents the cutting edge of rocket technology, with several Chinese companies already developing similar systems. It's worth noting that CASC is working on a particularly powerful version for their Long March 9th mega rocket project. These tests signal China's commitment to developing a diverse range of rocket technologies, from deep space exploration vehicles to heavy lift rockets. According to KSC engineers, this is just the beginning. They're planning to conduct even more research and testing of various engine types for China's major space projects, suggesting we might see several new Chinese rockets debut in the coming year. This coordinated testing effort demonstrates China's growing capabilities in space technology and their determination to become a major player in space exploration. With these successful tests, they're laying the groundwork for increasingly ambitious missions, from lunar exploration to potential Mars voyages. And that's it from me for this episode of Space Nuts. I'm Anna. Don't forget to visit astronomydaily.io for your daily fix of space and astronomy news updates. We're constantly updating the site with the latest discoveries, mission updates, and cosmic wonders. Until our next adventure through the cosmos, keep looking up and stay curious about the mysteries that surround us in space.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.